Welcome guys. So in this video, let's talk about famous part in the linear algebra. It's called the dual space. Okay, so many people like to say this, but I think up to now, the systematic approach is so I want to do a systematic approach for this dual space. Okay, so let me just give a definition. So given a two-vector space V and W, I can construct Hom VW. So basically, it's all the linear transformation from V to W. Okay, so Hom VW, just all the linear transformation from two-vector space V and W. Okay, so obviously that if you take two elements, let's say S and T, you can define addition. So S plus T. You can define S plus T act on V will be SV plus TV, right? So S, and then also you can check that if I define, yeah, so this is the definition, and easy to check that as X plus T is also linear transformation. Okay, right? And also yeah, you have also zero linear transformation, right? So basically you map any vector to zero. Okay, and so from here you know that this S plus T, sorry, this Hom VW with this addition will form the abelian group. Okay, and the next I can talk about scalar multiplication with a field F, right? So if I take any alpha belongs to F, then I can define alpha T, which is another linear transformation. T belongs to this, such that alpha T act on V is defined to be alpha T V. Okay, so basically, if you view this T as a matrices, you times any number will be another matrices, right? So which tell you that you can check all the axiom. This final results will be Hom VW is a vector space. Okay, so this is I think it's obvious. Okay. So so next theorem is people like to talk basically what is the dimension of this Hom VW. So remember that I already proved in the previous video. I proved that any finite dimensional vector space over field F is isomorphic to F, right, with some dimension. Okay. So results basically this is basically n let's say m times n. Okay, so m times n. So m is the dimension. So dimension of v is m. Dimension of w is n. Okay, so this is the main results that I want to prove. Okay. Okay, so in order to do this, we need to construct we need to construct a basis, right? We need to construct a basis in Hom VW. Okay, so let's say V1, V2 up to V M is a basis. So we pick up basis of W of V, and also the W1, Wn is a basis of W. Okay, and so you see any linear transformation from V to W is determined by what? So you see any vector in V, right, can be written as the lambda 1 V1, lambda 2 V2, up to lambda n Vn, right? So sorry, lambda m Vm. So your T of V will be lambda 1 TV1, lambda 2 TV2, lambda m TVm. Right, so the image is determined by so the linear map T is determined by all the map if you fix a basis. Okay. Okay, so now I can define a Tij, which is a linear map such that it maps V to W, such that this Tij maps VK0 for all k not the same as I, and this Tij map Vi will be Wj. Okay, so this is the map. Okay, so I construct a family of a linear map such that the Tij vk 0 if k not the same as I. If k is the same as I map to wj. Okay, so how many tj, tij, right? We have m times n tij, right? So results will be, I think you guys already guessed. So tij forms the basis of harm vw. Oh, okay. Yeah, so remember that so basically we will use this fact. So let's see. Okay, so let's see let's see we take S belongs to harm of VW, which is a nonlinear map. So we know that the SV1, right? So SV1 will be in W, right? So I also know that the SV1, right, is a, so W is a, W has W1 up to Wn as a basis, right? So I can write SV1 as alpha 1 1 W1 alpha 1 2 W2 up to alpha 1n Wn, right? And then all these coefficient in F, okay? And also, and then you just check that you can define SVI, right, as a alpha I1 W1 alpha I2 W2. This is just some notation. Alpha IN Wn. Okay. Okay. So yeah. So I from 1 to m. Okay. So I obviously that obviously what? Let's see. So obviously that okay, obviously that I can define S0. So what is S0? F0 just defined to be alpha I1. So each time you see W1, you replace as T11. So replace as T11. So it's alpha 11 T11 and alpha 12 T12, alpha 13 T13. Just keep going. Right. So you replace W1 as T11. W2 as T12 and W3 T13. Okay, so this is the first row. And the second row is start from, so second row, right, so SV2, start from alpha 21 W1, right? So alpha 21 W1 replace as alpha 21 T21, alpha 22 T22. Okay. Okay, so finally become like alpha M1 TM1 up to alpha MN TMN. So there's a lot of. Okay, and then you can easily check that this S0, right? You can easily check that when S0 act on V1. So okay, so when S0 act on V1, right? So this T11 T1 only survive when T1 act on V1, right? Because this Tij only survive when it maps to Vij, right? So by this stupid construction, you can see that S0 V1 is just the same as SV1, and the S0 V2 is the same as SV2, and the S0 VM is the same as SVM. So which means that the S is just S0s. Okay. So now I prove that I prove what? I prove that the S this Tij, right, spans whole harm of VW. Okay, so the remaining is to prove. So let me just clear, right? Let me just write clear. Okay, so what I'm saying is that this harm VW is spanned by Tij, right? It spans by a family. This spans by a family is Tij. Okay. Okay, so the remaining, so remains to show what? Show this Tij are linear independent. So since I already know that they can span the whole space, so remaining just to prove is linear independent. Okay, so Yeah, I think in a textbook that yeah, let's quickly see the linear dependence. So let's write. So suppose I get some Bij, which map Tij. Okay, so I from 1 to m, j from 1 to n is 0. Right, so I need to prove that all beta ij are 0. Okay, and then remember that we got this property that this is basically this, and this is basically 0 if k is not the same as I. Okay. Okay, so what do we do, right? It's very trivial, right? So let's put v. I think we just put v. We first put vk in it. Okay. So we get let's say we apply the vk, right? Okay, let's apply vk. Right, so we can apply vk to it. Okay. So what is this? Right, this becomes this becomes w. This becomes wj. This becomes wj, right? When k is the same as I. Okay. So this becomes you get what? You get only so when you run this I only I equals to k survive. So you get the beta kj, right? Beta kj wj, which is 0. Okay, so your I disappear, you're going to get j, right? But by definition, I know that wj is a basis. Wj is a basis. So you show that the beta kj is 0, right, for all k. Right, but this is independent, but for all so you fix k, and you get beta kj 0. Right, but this argument only works for all k. Works for all k. Sorry. So from this you get so you fix k, then you know that j from 1 to n will give you beta kj equals 0, right? But your k can start from 1 to m, right? So basically you prove that all the betas is 0. Okay, so the proof. Yeah, so basically once you get that, you get beta kj 0 from j 1 to n for your fixed k, right? But your k can be chosen from 1 to m, right? So all the beta kj is 0. Okay, so they are linear independent, and their span will be home. Yeah, so we prove this theorem. Okay, so let's do some corollary. These two corollary are also people like to say it. Okay, so previously that we proved that the harm of VW is isomorphic to f and n if this dimension is m, this dimension is n. Okay, so to corollary, which is also known, is that the harm VV is just m squared, and the harm of VF. Right, so once you view F is a one-dimensional vector space, right? So it's just F. Okay. So which is the dimension is the same as VE. Okay. So it has a real different name. So people like to say that as a definition. The definition is basically this harm of VF called the dual space. Dual space. Okay, so which is dimension is the same as the original vector space. Okay, yeah. So let me let's usually call it v hat. Okay, so v hat is basically all the functions from vector space V to a field F. Okay, and the basis, as what we said, is basically your basis called Fi, which you which if your echelon Vj, which V1 Vm is a basis, is defined to be delta Ij. Okay, so this means that 1 if I equals j, I the same as j. If I is not same equals 0. Okay, so this is called dual space. Okay, so the results basically says that if V is finite dimensional, then the V dual is isomorphic to V. Okay, yeah, this is the results. But let me talk about some interesting lemma. Okay. So this lemma is interesting. It says that V is finite dimensional, and you take V is non-zero in V, right? Then you can find the element F in a dual such that V is non-zero. Okay, so this is a strange, not a little bit. You need to think a little bit. It says that if you take a non-zero vector in V, which you can find another dual which maps is also non-zero. Okay. Yeah. I think. Yeah. So I think this one is basically not difficult. So you can yeah. Okay. Maybe just let me go to the quick proof. Okay. So quick proof is basically let's say if you get V1 up to Vn is a basis, right? And you can define what I'm saying. Which this is Fi, which are mapped to Vj defined to delta ij. Okay, so we can create this Fi. Okay, so once you have this, then obviously that your Fi act on the summation alpha j Vj will only give you alpha I, right? Okay, so once from this, that once from this, right? If V is not zero, then the V is non-zero, right? Then you can find the basis, right? You can find the basis. So you can find the basis, which start from V, right? Let's say you start from V, and you start from V, and then you create another V2, V3 to complete all the vector space, right? Up to Vn, right? And then you can just take such V hat, V1 hat, which act on V. This V1 hat corresponding to V, right? So yeah, so this is one. By construction. Okay. So basically, you just replace this Fi to be V1 hat, which is a dual basis of corresponding V1 hat. So it contains V2 hat, V3 hat, but the V corresponding to V1 hat by definition, V1 hat act on V should be 1. Okay, so this is just proof, almost trivial. Okay. Okay. So one can talk about a so-called second dual. So let me just quickly see. Yeah. So now start from here will be a little bit abstract. Okay. So let's define if you take any vector v0 in a V, right? And then you can define and then you also take a function which is inside the V hat. And you can define this TV0, right? TV0 is just a name, right? Act on F to be FV0s for any F belongs to V hat. Okay, so this TV0 is something strange function which act on the V hat as its variable, but the map to FV0s. So FV0 is what? It's just a number, right? So this is just in field F. Okay, so you can, yeah, this is just definition, right? But you see that if TV0s, and I define TV0s, act on F plus G, is basically F plus G V0, right? But F plus G is also linear, right? In the dual space. So this is F V0s plus G V0s. And also if you TV0s, if you act on alpha F, which becomes alpha F V0s, by definition is alpha V0s. Okay. So basically, you can collect of this TV0. So the amazing fact is that collect of these TV0s basically is the dual space of the dual space. So I should write the words is dual space of V dual. So I should write it as V dual dual, right? But by this construction, who should I tell you what? I tell you that there is onto map. There's onto map, right? From V to onto V dual dual, right? Because this is labeled by V0, right? So basically any V0 can any V zeros will forms a V dual dual, right? Yeah, so this is the map. This is called second dual, okay? So what I'm saying is that given a V in a vector space, right? You can create a TV in which is in a dual space or second dual. Okay, so you can construct a map such that just write down just V map to V dual by map to V into TV. Right, this is called psi map. Okay, the reason is that psi is obviously psi is homomorphism, right? You can check by yourself. So psi is homomorphism. So reason is that when psi is isomorphism. Okay. So let me see. So I think this is not true. I think I can say that you can only find the map from V to V second dual. It's not guaranteed that obviously now is a isomorphism or onto, right? I can only say it's homomorphism. Okay. Okay, so what is psi b isomorphism? So isomorphism means what? Means that if your psi v is 0, right? If your psi v is 0, or basically what it's saying is that TV is 0, right? So you need to ask when is TV 0, right? You hope to prove that when TV is 0, then V is 0, right? Okay, but let's see, if TV is 0, right? You can then 0 is basically TVF, which is FV, right? For all F belongs to V hat, right? But the problem is that we prove that V is non-zero, then you can always find F, which is non-zero. Okay. Okay, so we prove that the only case is that V must be 0, right? Because we prove that if V is non-zero, then you can always find F, which FV is 0. Okay, so what we prove is that in a finite dimensional space, your psi is isomorphism. Let me see. Yeah, I think this is, yeah, so this is true, right? Because we prove that if TV is 0, we prove that V is 0. Okay. Obviously, psi is isomorphism. Okay. So the reason is that, I mean, this is the hardcore proof, right? But I mean, if you work in the dimension proof that the V dimension is a V dual is still M dimension, and then you dual is still M dimension, right? So V is isomorphic to M V dual. Okay, but for the infinite dimension, though, that it's not indeed true. Okay. Okay, so let's talk about another interesting idea called the annihilator. Okay, so this is also talking the commutative ring theory if you are interested, but we talk about vector space. Okay, so you take a subspace of V, and then you can define all the called annihilator of W, basically it's A of W, which is all the linear transformation, basically belongs to harm of so linear transformation in the dual, so basically harm of V F. Yeah, so this is a subspace of dual such that T of V, or basically F of V is 0 for all V belongs to W. So which is all the linear map such that it will annihilate all the vectors in W, which is a subspace. You can prove that obviously a subspace of V dual. Okay. Okay, so simple exercise is that this is a subspace of V dual. Okay, so use your simple linear algebra. Okay. Okay, yeah. Okay, so let's invest some property. So if the W view is a subspace of V, right, and the V is a finite dimensional, then for each V, for any let's see. So for each F, right, defined on the V dual, right, then you can restrict this V to to W, right? So basically, you can restrict V econ W, right, divided by F tilde, such that this F tilde W is just FW, right? For basically for all W in the W. Okay. Okay. So let's see, right? So this is a definition. So let's see. So obviously we can define a map T from V dual to W dual, right? I didn't talk about W dual, right? Because I restricted into W. Right? I restricted any linear function node on V restricted to W. So I create a dual linear map from dual. Okay, and obviously this is homomorphism, right? By definition. So you can ask what's the kernel, right? What's kernel T? So the map, this map just restricted, just restriction. So I just write down. So if map F is map into V dual, basically it's V restricting on W. Okay, what's the wise kernel? No, so this is the restriction map, right? So this is a restriction map. So if the kernel, if the element is inside the kernel, so that means FW is 0, right? For W in W, which is by definition is annihilator, right? So the kernel of T just exactly AW. So this is a definition. Okay, now this is a restricted map, right? So your idea should be you should intuitively think this is the onto map. Okay, so claim T is onto. Yeah. So let's quickly see why T is onto, right? So let's see you take H belongs to W hat, which we need to. I want to claim that H comes from restriction. So H comes from restriction. So you can find some F, which is in a V hat, such that you believe that when F belongs to V hat, such that F restricting to W will the same as H. Okay, so this is a goal. Yeah, this is not difficult, right? Because that if you take the basis W from 1 times Wm, right, by our previously that you can find another vector W1 V1 to Vn such that it complete or VR such that VR completes as a basis of V, right? Okay, so let's call the span of this space W1. Okay, so from this, we know that the V is a span of this W direct sum W1, okay? Okay, so this means that any vector V, so any vector V can be written as W plus W1, right? W in the W, W1 in W. Okay, so once you have this, then you know that your F of V, right, will be the same as FW, right? This is so this is the construction. Let's see. Sorry about it. So let's see. So we got V equals to W plus W1, right? So let's say you have a function F divided by defined to be V hat, right? So your V dual, so your FV by definition, right, will restricted the map, will restricted to a W, right? Will restricted to a W. So we need to find this F, right? We start from H and find F. Okay. So what I'm saying is that I can define F easily. I define F to be F econ V, the same as H econ W, right? So this is the trick. So for each F, I define such. For each H, I define such F such that F econ V is the same as H econ W. Okay. So easy to okay. So right from here that you know this map is onto, right, because I can construct F, which when F restricted to W, it map to it's the same as this HW. Okay, so we got T from V hat map to W hat, which is onto, and then the kernel of T is basically an annihilator. So from the group isomorphism theorem, the first group isomorphism theorem, your T quotient your kernel will isomorphic to W hat, which tell you that the V dual map to the quotient A annihilator of W will isomorphic to W hat. And you take dimension, right? You take dimension, so this is dimension M. Let's say this is let's see if this is dimension N and this is dimension M, right? And this is the dimension isomorphic W. So the dimension of annihilator must be N minus M. Okay, so this is, I think this is another accomplishment that we prove that the annihilator is not actually we not only know it's a subspace, but we also know its dimension. Okay, so there's a query. Okay, so this query is a very weird one. So AW is what? AW is what? AW is an annihilator, right? If you take an annihilator again, you come back to W. Okay, so this is the proof. The proof. So if W becomes V, right? And then you know that your AW, right, will becomes V dual, right? You just use the theorem again, right? Because we proved that AW, so this will replace AW becomes AV, right? Which is sorry, not AV, which is you know that AW become a V dual, right? By construction, and you take A again, you get AAW becomes a also with second dual, right? Okay, so yeah, now we have proved that in finite dimensional V is the same as V dual. Okay, so right. So we prove that if any element belongs to X in W, then it creates this space with a subspace of V. So which tell you that this statement tell you that W is a subset of AAW. Okay, right? Because we prove that in each start from here, you arrive here, right? So the element inside this must inside this. Okay. Yeah. So we need to show it back, right? So we want to put it back. So let's see. If W belongs to W, then your psi W is basically TW. So remember, psi is what we already defined with, right? You define to be this T. Here is TW egg on F will be F egg on W. Okay. And let's say if W is W, right? So this psi W is TW, TWF egg on FW. Which is 0, right? For all F belongs to AW. Right, so this is true, but the dimension results tell you what? The dimension tell you that dimension of AAW is basically a dimension V hat minus dimension AW, right? By the previous results. So dimension V hat is M, let's say N, and the dimension AW is already proved. Basically, it's a dimension V minus dimension W. Right, so this is dimension W. So now we have a subspace, a W, which is a subspace AAW, but they are the same dimension, right? So what we show is that the dimension AAW. So you see, in the linear algebra, that dimension is so powerful too. It's the same as W, right? But they are contained in each other. This W can contain this, but they have the same dimension, so they must be equal. Okay. Okay, so we prove these results. Okay, so okay, so we can prove the linear algebra results by using this. Okay. So let's talk about. So there is a theorem says that right, if you get some stupid linear equation, a linear system, such as x1 up to xn is 0. Okay, so this is the result, and this is rank R. Okay, then the solutions, the fact is that there are n minus R linear independent solutions in Fn. Okay, so this is a theorem. So basically, you got some strange linear system, recurse R, and then you are proving that there are -1 linear independent solutions in vector space. Well, this is basically high school results, right? But okay, but how do you actually prove? Okay, so suppose I get these such systems, right? And that's right. So that's okay. So this is okay. So let's see. Let's define a solution to be. Let's define. Let's see. Okay, so let's see. U is generated by the vectors. So U is a span of this coefficient. Let's say A11, A12, right, up to A1n, and A21, A22, up to A2n. And this is all the vectors, a span of this. Right? So you get the AM1 up to AMN, right? So basically, you take all this coefficient, right? All this coefficient as a span, right? You span a vector space. Okay, which is a subspace of the Fn, right? So, and the rank means the dimension of U is R. Okay. So by the previous results, we know what? We know the, yeah, I mean, this is the definition. Okay. Okay, so let's define, let's say I take V1 to be the standard 1, 0, 0, 0, 0. V2 is 0, 1, 0, 0, 0. Up to Vn is 0, 0, 0, 1. Okay. Okay, so and I take the dual, so V1 take the dual. Okay, also dual. So we know that this dual is a basis in the F dual, right? Fn dual. And for any small f belongs to F dual, this F is basically writing X1 V1 dual. Okay, X and Vn dual. Okay, so so I want to ask when is what? When is such f, right? So such f belongs to AU, right? So this AU is an annihilator of U, right? Annihilator of U. So basically, it's construct all the linear map, all the homomorphism, so all the linear map. So I want to AU is a subspace. Remember, we proved that AU is a subspace of F and U, right? So I want to ask which F will have these results. Okay, so obviously that you just what? You just take zeros, F econ A11, A12 up to A1n, right? You just take all the coefficients. You just take all the. Okay, so let's see. Sorry. So suppose A11, A1. We know that A11, A12 up to A1n belong U, right? So your F econ list should be 0. Right? So which is X1 V1 hat, X2 V2 hat, up to Xn Vn hat. Econ A11 V1 up to A1n Vn is what? Is 0, right? So by computation, this is X1 A11, X2 A12 up to Xn A1n, right? Which is 0. So which is just a linear equation. Okay, and you know that the Vi, you know that your Vi hat Vj is 0, right? For I not same as j, then your Vi hat Vi is 1. Okay, this is the so this is what we use, right? So we can prove this. Okay, so obviously that what we show is what? What we show is that when we have a linear equation, which when we have a solutions, we get AU, right? So I should say that each solutions is an element corresponding to element. I should say correspond, right? Because so each element x1 from xn will construct a dual, right? So which corresponding element in AU. So actually, obviously that all the AU, right, become each solution. So all the solutions become AU. Okay, so what I'm saying is that the solutions forms form AU. Okay, which is an annihilator of U. Okay, and we prove what? We prove the dimension of the annihilator U is the dimension of the original vector space N, right? Minus the dimension of U, which is R. So it's N minus R. Okay, so this is just a linear algebra application. I think it's very astonishing. Okay, so see you guys next videos. Bye.